So questions about calculus, first of all, because tomorrow is the calculus final, and then we'll have Maple and algebra. Any questions? Everyone just come to listen to other people's questions? Anything?
Over problems 13 and 14 for the final.
Which course? What class are you in?
155, the
Okay.
calculus laboratory.
So let me take a look. All right, so I'm looking at the Math 155 review. What questions did you have?
13 and 14.
Okay. So let me open up a Maple window. I'll continue with this. Okay. So we want okay. Problem 13.
Yes, sir. Problem 13
Okay.
and 14.
So if you're going to use implicit plot, you have to open the plots package. So you type with plots. And now all of these commands are available. And here's implicit plot, so we can use it. And we want to graph this curve. So it's just implicit plot. And you type in the curve, x squared minus 11 times x times y plus 2 times x squared equals 22. And then you need to give a range of values for x and y. So I'll just pick something at random and then I'll change it if I have to. So they say x goes from minus 10 to 10, and y goes from minus 10 to 10. So that's the syntax. And I have to spell plot correctly. Oops, that looks like it's right. Ah, so there it is. It's the hyperbola. Any question about that? Or anyone else have a question about that?
Yes. So unless I put with plots, if I don't put that command in, I won't be able to use implicit plot, right?
Correct.
Okay.
Correct. So some commands in Maple are available as soon as you turn on Maple. But Maple is a huge package, and they're collections of commands for different areas. So for plotting, if you just use the command plot, you can just use plot. That's immediately available when you start Maple. But all of these other plotting commands, if you're going to use them, you have to tell Maple you're planning to use them. And this is the command to open this package of plots. Okay. Then you also asked about problem 14. So we want to compute a certain sequence of integers, and it's defined recursively. A1, we said equal to 3. A2, we said equal to -2. And then we write a loop. We have the first two, so we can start for n from 3 to 20 do. And I always like to put in my n do. And now I want to define the nth term of the sequence is going to be equal to the n minus first term minus the n minus second term. That's the recursion relation. And here's the sequence. It's periodic. Period 6, as it turns out. 3 minus 2 minus 5 minus 3, 2, 5. And then 3 minus 2 minus 5 minus 3, 2, 5 again. And the 20th term is -2.
Professor, how exactly did you get that that arrow to appear before the command?
Sorry, how did I get what?
That red arrow to appear before the command, a bracket
So,
1 close bracket. How did you?
You don't have one. You go to this command bar at top, and this symbol, do you see where the cursor is pointed?
Yes, sir.
Okay, if you click on that, I'm clicking and clicking, I'm getting all these different command bars. Now, when you open Maple, if you go to File, New, and you have a choice, Worksheet mode or Document mode. If you choose Worksheet mode, then these red arrows, these are the command prompts, will come up automatically. If you choose Document mode, then you're going to have to insert them yourself. But we never use Document mode, so you can just use Worksheet mode. That's usually the default.
I'm sorry.
Professor,
Could you?
Yeah. Do you have another question about this problem? Then I'll go on to someone else.
Yes, I was just wondering if you could just scroll back up a little bit so we could see the command, the entirety of it.
That's all it is. Again, I saved the video and I posted it to YouTube, so it's available.
So you're going to be posting this review session?
Yeah, yesterday's session is also posted.
Oh, okay.
Professor, could you go over question number 10? Math 155.
Sorry, number 10 in what class?
Math 155. Uh, 155, Professor.
Sorry?
155.
Yeah. So to find the local minimum and maximum and inflection
Yes.
points?
Yes.
Okay. No problem. So we have this function. F of x is the square root of x to the fourth minus 7 times x squared plus 17. It's always nice to know what things look like. So let me just plot f of x before I even start the problem. You don't have to do this, but it's nice to do it. That's what it looks like. Suppose I plot it maybe just from minus 5 to 5. Okay. That's what it looks like. Now, this looks like it's touching the x-axis, but it's not because, well, maybe it is, but it's probably not. We'll see. Okay. So to find the local minima and maxima, we need to find the derivative of the function. And then we need to know when is this derivative equal to 0. So what we really want to do is f-solve the derivative of f of x equals 0. Solve that for x. It says we have one solution, but you have to be careful because f-solve doesn't always give you all the solutions. So let's just check and see what the derivative looks like. Suppose we plot the derivative of f of x. It looks like there are 3 solutions. One of them is 0, but there are 2 others. So one of them is positive. So we could say, okay, let's look for a solution maybe between 1 and 5. I get it. I get it because I know I'm looking at the curve. That's why I'm doing this. And there's also a negative solution. And the negative solution looks like it's between minus 5 and minus 1. So let me look for a solution there. So I have 3 critical numbers. Let me just give them names. This is, say, critical number 1. This is critical number 2. And this is the critical number 3. So the derivative is equal to 0 at 3 places. And I want to know if they're local minima or local maxima. So I can use the second derivative test. So let's just write this as a note. Use the second derivative test to determine local maxima and minima. So what is the second derivative? That's the second derivative. Oops. Let me do it right. This is the second derivative. And let me evaluate this at the 3 critical numbers. So if I evaluate the second derivative at the first critical number, I get something negative. So that tells us that Cn1 is a relative maximum or a local maximum, same thing. What about the second critical number? It's positive. What about the third critical number? it's also positive. So I can make the following comment. CN2 and CN3 are local minima. And of course, that makes the perfect sense because we see from the graph, you have a local minimum, then a local max, and then a local minimum. So that's how you find the local minima and maxima. Right? Any questions about that before I do the next part of the problem?
Yes, I have a question, Professor. Is there any way we can determine the critical points without using a plot? Uh, so F-solves gave us just one solution. Is there any way to get all three solutions without using a plot?
Not that I know of.
So we have to use the plot and use the limit of x all the time?
Right. So what we've seen in many problems in the course of the semester is that F-solve does not always give all solutions of an equation. And you need to look at the plot and visually determine approximately where other solutions are, and then you can use F-solve to find them. But it won't do it without your help.
Okay, understood.
All right, and then we need to find the inflection points. But for the inflection points, we have to find the zeros of the second derivative. So we want to F-solve the equation. Second derivative of f of x equals 0. Solve that for x. And we get 1 point. Now, what is the second derivative? Second derivative, that's the second derivative. Let's see if we could even simplify this. I'm just sort of curious. Yeah, that's the second derivative. Well, this might not be every solution. So let's just check. Suppose we plot the second derivative. So when you plot it, you see there's two solutions, one positive and one negative. And F-solve just gave us the positive solution. So to find the negative solution, looks like it's between, let's say, -2 and -1. So let's just look there, x equals -2 to -1. So we have a second solution. And if you look at this plot of the second derivative, you can see it's positive up to this point. So it's concave up here. From here to here, it's negative, so it's concave down. And over in this direction, it's always positive. So the concavity changes at these 2 points. So we can say that f of x has inflection points at these two numbers. And that's the solution of the problem. Okay. All right, well, any questions about calculus or algebra? We can come back to Maple later, but let's give other people a chance.
Hi, Professor.
Yes?
Can you go over question 13, algebra?
Okay. Maybe find the review sheet.
Professor, which one are you doing now?
So this is
Oh, okay, okay.
the algebra review sheet,
Okay, thank you.
number 13. So we have the permutation sigma 1, 3, 4, and the permutation tau, which is 2, 5. And we want to prove sigma tau equals tau sigma. So you can just do the calculation. Let's do it and write down the standard form for the permutation. 1 goes to 1 goes to 3, 2 goes to 5 goes to 5, 3 goes to 3 goes to 4, 4 goes to 4 goes to 1, 5 goes to 2 goes to 2. So that's sigma tau. And tau sigma one goes to 3 goes to 3, 3 goes to 4 goes to 4, 2 goes to 2 goes to 5, 4 goes to 1 goes to 1, 5 goes to 5 goes to 2. Oops, let me just double check this. 1 goes to 3 goes to 3, 2 goes to 2 goes to 5, 3 goes to 4 goes to 4, 4 goes to 1 goes to 1, 5 goes to 5 goes to 2. And you look at them and you see they're the same. So for these particular permutations, you have commutation. Now,
I have a question.
yeah,
Is not 4 going to 2?
sorry,
4. Go to 2.
1,
4.
4. So this sends 4 to 1, and this sends 1 to 1, so 4 goes to 1.
Okay.
This permutation sends 4 to 1. This permutation sends, so this is under sigma, and under tau, 1 goes to 1. So 4 ends up at 1. Right? This sends 4 to 1. This sends 1 to 1. So under the composition of functions, 4 goes to 1 goes to 1. Just that. Okay. So definition of disjoint cycles, suppose we have the cycle A1, A2, A3, up to, let's say, A sub k, and another cycle, let's call this one sigma, and say tau is a cycle B1, B2, up to B sub L. So this is a K cycle, and this is an L cycle. So sigma and tau are disjoint. This is the definition. If these numbers are different from all of these numbers. So if AI is different from BJ for all I going from 1 up to K and J going from 1 up to L. These numbers and these numbers, they don't share any numbers, nothing in common. So for example, sigma and tau, right? These are disjoint. Because here we have 1, 3, 4, and here we have 2, 5, and we have different numbers in those two permutations. All right, that's the definition of disjoint. And how do we prove that disjoint cycles commute? So you just write things down carefully. So suppose that sigma, A1 up to AK, and tau, B1 up to B sub L, are disjoint cycles in the symmetric group Sn. So what is sigma tau of X? Well, there are three cases. So case one is X equals AI for some I. So X is one of these numbers. So, or let's just say, so in that case, tau of AI is equal to AI because AI is not one of these numbers. And so sigma tau of AI is sigma of AI. On the other hand, let's call this something a sub I plus 1. Right? It's one of these numbers. Also, sigma of AI is this AI plus 1. And so tau sigma of AI is tau of AI plus 1. But AI plus 1 is a number over here. It's not one of these numbers. So this is AI plus 1. So sigma tau of AI equals tau sigma of AI for all I from 1 up to k. In case 2, let's say X is equal to some bj. So we have tau of b sub j is b sub j plus 1, and sigma tau of bj is sigma of b sub j plus 1, but that's not one of these numbers. So this is just b sub j plus 1. And on the other hand, sigma of bj, again, it's bj because bj is not one of these numbers. And so tau sigma of bj is equal to tau of bj, tau of bj, which is bj plus 1. So we end up at the same place. So sigma tau of bj is tau sigma of bj for all j from 1 up to L. In case 3, X is some number C, which is different from all the AIs and BJs. And in that case, sigma tau of C is sigma of C, because sigma and tau leave C fixed, is C, which is tau of C, which is tau sigma of C. And again, everything commutes, and we're done. And that is how you would write out a formal proof of this assertion. Yeah. That's what it is. Are there questions about that? This is what you have to learn in Math 314, how to give a proof of a mathematical statement. Any questions from Math 175? Yes, no?
Professor, I have a question, but you could take another course and then come back to me.
Any questions from Maple? No?
Yes, sir. I have some Maple questions.
Go ahead.
I was hoping you could do 16 and 18.
In Math 155?
Yes, sir. Math 155.
Okay, let me get back to a Maple screen. Okay, number 15?
No, sir. 16.
Number 16. Okay. Let me do 15 and 16 both because you can't do one without the other. So if you just want to list the prime numbers of that form up to n, you would say for n from 1 to 100 do. Let me write my n do. And now I only want to list the numbers that are primes. I don't want to list anything else. So if n cubed plus n plus 1 is prime. So this is my Boolean function. This gives you an answer, true or false. Then if it's true, let's print out n, so I know what the n is, n cubed plus n plus 1. And then I have to write end if. So this program should write out all of the primes of this form. And there they are. Okay. But in problem 16, I don't want to write them out. I just want to count them. So I need to modify this program a little bit. So let me introduce a variable that will just count the number of the primes. I'll call it capital N. So in the beginning, I set it equal to 0. And so now here's what my program should do. If n cubed plus n plus 1 is prime, then increase this number n by 1. That is, write n equals n plus 1. So now every time this is a prime, I add 1 to this counting number. And when I'm all done, let's say I print out, there are n primes. So there are 31 of them. If I don't want to see the n equals 0, just I put a colon instead of a semicolon, and I just get the answer. All right. Any questions about that?
Yes, sir. I have a question about the print portion.
Okay.
How exactly am I supposed to input that? Like, am I supposed to put a space after it or after the end do? Because right now I'm getting an error when I try to.
No, there doesn't have to be. If it's on the next line, there doesn't need to be a space. But if you have spaces, like if you had a space here, right, where I just introduced spaces, you're going to get an error. But there can't be a space when you have a function and you put something inside parentheses. You can't have a space there. But what does the error say?
It says invalid argument sequence.
Well, so take this line and get rid of it and see whether the program runs by itself, if that part's okay.
I get n equals 0.
You shouldn't get anything. All right, there should be 0 output. So all I'm asking you is, does this run? Did you get an error message?
I had a semicolon instead of a regular colon. Okay, now I get nothing, yes. I had a semicolon instead of a regular colon. It was my mistake.
Right. So does it all work now, or is there still a problem?
Yes, sir, it does work now. I get nothing.
Okay, good. I mean, computer programming languages require precision. I mean, you might understand what you're doing, but if you write a semicolon instead of a colon or some other space where there shouldn't be a space, you haven't written the program correctly and you'll get an error. Did you have another Maple question before I go back to algebra?
Yes, sir, I had asked about 17.
Okay, so there's this function which produces a random 12-digit number, and that's the way it's written. All right, so you just enter this and you get a number. If you do it again, you get a different number. If you do it again, you get a different number because it's choosing a random 12-digit number. And if you want to make a list of 10 random 10-digit numbers, let's see, let me try it in two different ways. So for n from 1 to 10 do, I put in my n do. Let's see what happens if I just write this. Ah, it works. That's all. This just says for every n from 1 to 10, write a random 12-digit number, and here's a list of them. And you'll notice if I run the same program again, I get a different list of numbers. Because at every time this function operates, it's randomly picking a number. Okay. Any questions about this problem?
No, sir. All clear. Thank you.
Okay. Algebra. Any more algebra questions?
Yes, 26 and then 28. I know we did 20. Oh, no, wait. I know we did 27 yesterday. Hold on. No, we didn't. So 26 and then 28, please.
All right. So this is algebra. Problem 26. We let C star be the multiplicative group of non-zero complex numbers. And we define f sub n from this group to itself by f sub n of x is just x to the power n. So if you take any two complex numbers, fn of xy, that's xy to the n. But for complex numbers, that's just x to the n, y to the n, which is f sub n of x, f sub n of y. So f sub n is a group homomorphism. And we want to find the kernel. So the identity element in this multiplicative groups is just the complex number 1. So the kernel of Fn, it's all complex numbers call it Z, doesn't matter, Z in C star, such that f sub n of Z is 1. That means all complex numbers such that Z to the n is equal to 1. And if you write a complex number Z, you can always write a complex number as, if the absolute value is R, then Z is R times cosine theta plus I sine theta. And we can write this as e to the I theta. This is r e to the I theta. So z to the n is r e to the I theta to the n. That's r to the n e to the I n theta. And the absolute value is just, this has absolute value 1. This is just the absolute value of r to the n. That's 1. So r equals 1. So anything in the kernel is going to be of the form e to the I theta, which is cosine theta plus I sine theta. That just means it's some point on the unit circle. So this is the unit circle in the complex plane, all the numbers with absolute value 1. And we want to know for which numbers on this circle is z to the n equal to 1. So, but z to the n, that's e to the I theta to the n. This is e to the I n theta. And that's equal to 1 if and only if n theta is a multiple of 2 pi. Right? You go around 2 pi, you get to 1. 2 pi k. So theta is 2 pi k over n. And what this corresponds to is if you take the regular polygon with n sides, so this angle is 2 theta over n, and this is 2 times that, and so forth. That's what the kernel is. It's what are called the nth roots of unity. It's all z, where z to the n is equal to 1. I mean, you could stop right here if you like. I mean, this is the kernel. It's all complex numbers where z to the n is equal to 1. But if you understand complex numbers, then it corresponds exactly to the vertices of this regular polygon with n sides inscribed in the unit circle. But that's what it is.
Got it. Thank you.
Did you have another algebra question?
Yeah, I asked about 28 also.
Okay. So this is just like from calculus. In problem 28 in the algebra review sheet, R is the additive group of real numbers. That just means you add the numbers. And R with a greater than sign, this is the set of positive numbers, and that's a multiplicative group. And we have the function exp from R to the positive numbers. Defined by exp of x is e to the x. And you know from pre-calculus that exp of x plus y, that's e to the x plus y. But just from the rules of exponents, this is e to the x times e to the y, which is exp of x times exp of y. And this means we have a group homomorphism from this additive group to the multiplicative group. and there's an inverse, there's a function log from the positive numbers to all the numbers defined by log of x is just log x, the usual natural logarithm. And you know that the log of a product is the sum of the logs. So you, in this multiplicative group and this additive group, here this means you have a homomorphism. And you know, one is the inverse of the other because the log of exp of x is the log of e to the x, which is x, and exp of log x is e to the log x, which is x. So exp inverse is the logarithm. If you have homomorphisms from one group, from a group to a group and another in the opposite direction, and if the compositions are the identity, that means you have an isomorphism. So that's that problem.
Thank you, Professor.
Okay. Anybody here from Math 175, calculus? Any calculus questions? We have time for another Maple question if there's one.
Yes, sir, Maple.
All right.
Could you please do question 19 on the review sheet?
Take a look.
I'm sorry, I meant 20, sir, I'm sorry.
Okay, that's a nice question. So let me find the Maple worksheet again. So this is Math 155, problem 20. And just the way there's a random number generator, there's a function called rand poly, which generates a random polynomial, degree 5 usually. You have to say what you want the variable to be, so let's call it x. So this function generates a random 5th degree polynomial. You can see if I do it again, I get a different polynomial. I mean, if I do it 10 times, oops, forgot the x. Yeah, I just get, every time I get a different polynomial. And okay, so in problem 20, I want to generate a random polynomial and study it. So let's call it f. Actually, I'll call it a to start. So there's a random polynomial. And let me turn it into a function of x. So f is going to be the function. Actually, I don't even need, let's make some more complicated. Let me try it like this. Here, well, I get another random polynomial. So let me just copy and paste. So now I generated a random polynomial, and I want to find its relative maxima, relative minima, and so forth. Just because I'm always curious, let's see what the plot of this function looks like. Looks like that. This is already down to 800,000, so maybe I'll just graph it from -5 to 10. Yeah. Okay, well, so how do you find relative maxima and minima? You have to look at the derivative of the function, right? That's the derivative. The derivative of a polynomial of degree 5 is going to be a polynomial of degree 4. Let's try and find the critical numbers. So solve the derivative equal to 0 for x. And it gives us 4 different solutions. 1, 2, 3, 4. So these are the critical numbers. I'll call them Cn for critical number. So for example, Cn1 is the first. And this would be Cn2, Cn3, and Cn4, and so forth. And we want to know which of these is a relative maximum and which is a relative minimum. It's not clear what's going on in here. I'm just let's blow this up a little. Let's graph this maybe from -2 to 4. Even -2 to 2. Yeah, so it looks like maybe here there's a max, here there's a min, here's there a max, then there's a min down there somewhere, just to get an idea of what's going on. But in any case, we have the critical numbers, and how do we know if there's a maximum or minimum? Well, if you use the second derivative test, d at 2 of f, that's the second derivative, and I want to evaluate it at each of these 4 numbers. So let me just write a maple loop that will do it all for n from 1 to 4 do. And what I want to do is evaluate the second derivative at the critical number. There are 4 of them, right? So this says, for each of these 4 critical numbers, compute the second derivative. Well, negative, positive, negative, positive. So what that tells us is that, maybe just to make it clearer, n comma. So we have relative or local maxima at Cn1 and Cn3, because here the second derivative is negative. So maximum, and relative minima at 2 and 4. So we just found the first part of this problem. Where does it have maximum and minima, relative maximum and minima? What about inflection points? Well, to find the inflection point, you have to look and see where the second derivative is negative or 0 or positive. So F solve, so these will be inflection points, IP equals second derivative of x equals 0, solve for x. And we get 3 inflection points, and I could look at the sign of the second derivative, but it's clear if you look at this picture. Let me actually blow it up a little bit more. So maybe from minus 1.2 to 2. So yeah, when you blow it up like that, you can see here the curve is concave down. Here at minus 0.4, there's an inflection point. It becomes concave up. Here, at 0.08, that's right about here, there's an inflection point. So concave down, concave up, concave down, and then out here at 7.2, you can't see it on this graph, it turns concave up again. So these are the inflection points. And to compute the indefinite integral, that's you want to integrate f of x comma x equals int with a lowercase I the integral of this 5th degree polynomial is always a 6th degree polynomial. All right. So that's problem 20. Questions about any part of that?
Yes, Professor. I have a question about the could you scroll back down, please? Yes, for the F solve portion, right? Cn F solve, right? Are you always going to get 4 outputs?
Depends on the function.
Oh, okay.
This function has this particular polynomial has 4 critical points. Now, a polynomial of degree 5 will always have 4 critical points, but some of them might be complex numbers, so you won't see them. And some could be like double roots or triple roots. So you don't necessarily get 4 different real numbers. It depends on the function.
Okay, then I see.
Right.
Any other questions? Not from Maple?
Hello?
Yeah.
Oh, Professor, there will be more problem sessions, right? Aside from this one?
Yes.
Okay, and question.
Math 175, the exam is tomorrow, so there won't be any more for calculus. But for Maple and for algebra, there will be several more.
Gotcha. And if we would like to meet with you for a separate office hours as well, is that possible if we just send you an email?
You have to send me an email and give me times when you're available.
Gotcha. Okay, Professor. Thank you.
Okay.
Professor, I had a query regarding the review. I have completed the review by myself. Can I send you the document so you can tell me if I did anything wrong?
No. I can answer questions during the Zoom sessions, but I can't go over the homeworks problem by problem
Okay,
because I have, 100 students and many hundred problems I would have to look at.
I understand, Professor. And for Math 155 final exam, how many questions are we going to have on the final exam?
Maybe 10.
Okay.
That's the order of magnitude, at least.
Professor, will there be another session tomorrow?
Tomorrow, I'm giving, there won't be a session tomorrow, but there will be on Thursday.
Is there a set time for that session then?
Well, there will be. Let me just, I don't know if I can make it yet. It depends on various things, of course. Let's see. Yeah, on Thursday, it would probably be 12 to 1. Around 2 o'clock. But I'll send out an email. We have some math department meetings on Thursday, so I have to figure out exactly when those meetings will start and stop. But probably around 2 o'clock on Thursday. But sometime tomorrow, I'll send an email to everyone. Someone asked whether I solved problem 17 on Maple. And the answer is yes. Let me find it. Yep, this was problem 17. This is this function rand parentheses that produces a random 12-digit number. And if you want a loop to produce 10 of them, this is all it is. It's basically this one-line program. Okay. Any last minute questions before we go? I thought this was going to be from 1 to 2, but it's run on a little bit longer. But any last minute questions?
Can you do 17 algebra?
Okay, let me try. So I think I did that yesterday, but I'll do it again quickly. So I said there's a typo because we're looking at the group gamma 20. It shouldn't have said gamma n. So this is a cyclic group with these 20 elements, E, and then the first 19 powers of A. Of course, the 20th power is equal to the identity. And if you define a function from the cyclic group to itself by f of any element x is x to the 10th, what is the kernel in the image? So the kernel of f, this is all x, such that f of x is the identity, which means all x, such that x to the 10th is the identity. But the elements of this group are just powers of a. So this is all a to the k, where a to the 10k is the identity. And what is a to the 10k? Well, there are two possibilities. If k is even, like k is equal to 2 times L, then 10k is 10 times 2L, or 20 times L, and a to the 20th is the identity. So this will be the identity if k is even, and if k is odd, so k equals 2L plus 1, in that case, a to the k is a to the 10k is a to the 10 times 2k, 2L plus 1, because k is 2L plus 1. That's a to the 20L, a to the 10. This is the identity, just get a to the 10. So what you see is, so this is a little computation. You compute this. So the kernel of this function f, it's all a to the k, where k is even. So e a squared, a to the 4th, a to the 6th, up to a to the 18th, the even powers of a. And so the cardinality of this kernel is 10, because there are 10 even numbers from 0 to 20. In the image of f, you either get e or you get a to the 10th. And the cardinality of the image is 2. So that's part A. A question about that? Yeah. I do post the video on YouTube. Someone asked that in the chat. Okay. Let me just do one more part of this problem and then I have to stop. So we're still looking at the cyclic group gamma 20, and we have this function homomorphism from gamma 20 to gamma 20 defined by f of x is x to the 5th. So f of a to the k is a to the 5k. And that equals the identity if and only if 5k is a multiple of 20. That is, 5k is congruent to 0 mod 20, or you can divide everything by 5. K is congruent to 0 mod 4. So the kernel of f is just a to all powers that are multiples of 4. A to the 0, a to the 4th, a to the 8th, a to the 12th, a to the 16th. The next multiple of 4 is 20, which is back to the identity. So this is the kernel. It consists of these 5 elements. What is the image of F? This is the set of all things of the form f of a to the k, where you look at all possible exponents. That means everything of the form a to the 5k. And what are the things that you get? You get, when k is 0, you get the identity. You get a to the 5th, a to the 10th, a to the 15th. You're getting all the multiples of 5. A to the 20th brings you back to the identity. The kernel of F consists of these 4 elements. Sorry, the image of F consists of these 4 elements. All the powers of A, where the power is a multiple of 5. That's the image. Okay. Any questions about this?
Thank you.
Okay. So I'll schedule another review session for Thursday, but I don't know what time yet. I'll send out an email tomorrow sometime in the afternoon. Okay.
Okay.
Okay, everyone.
Professor,
Yeah.
I have a small question about the exam, algebra exam. So in the exam,
Sorry, wait, hang on. I didn't hear what you said. You have a question about what?
algebra,
Okay.
question about the exam. The thing is, you told us to do the six questions, right? On the exams?
Yes.
Yeah, but I did 6 and 7. So how you choose the questions? You
I
choose the
just did the
question.
first 6.
Oh, first 6, right?
The first 6.
Oh, so you don't choose the best answer in there.
No.
Wow, that's why I think.
I grade 6 questions and I stop.
Oh, I made some mistake in there because I did 7 questions, I think. So 1 or 2 questions are not such accurate. I know how you choose. That's why I didn't get a good grade. I thought you choose the best answer in there among those.
Nope.
So
But there is still plenty of extra credit on the exam. So it was easy to do well.
yeah, but I solved 7 questions over there. So I thought you choose the best 6 in there.
Well, I don't know why you thought that, but the instruction said do 6 problems.
Oh, okay.
That's all. It was
What
simple.
about you did better in the last 6 question? Is not count the last questions?
Well, if I say do 6 questions, you're not supposed to do more.
So you mean when you said for the first? So you mean the first 6 questions?
Yeah. I start to grade your exam. When I get, some people do less than 6, but if you do 6 questions, when I grade the 6 questions, I stop.
What about the rest? I mean, if we do better in the rest, like
It doesn't count. I said do 6 questions. There's already a huge amount of extra credit just doing 6 questions. You know, the first instruction was to read the instructions. and it said do 6 questions. That's fine.
Okay.
I mean, there was already like how much? Like a 20%. They're like 20% extra credit points just doing 6 questions. That's all.
What about the final? You will do the same thing?
Probably not. Probably there won't be a choice. The final will just be a list of problems and you can do them all.
And is there any extra credit?
There's always extra credit on my exams.
How many questions will be there in the final, Professor?
I don't know.
Because it's only 2 hours, you said, 8:30 to 10:30.
Right. Correct. So there could no more than 10.
You will give us more time?
No, final exams are 2 hours. There'll be a little bit of extra time because it's on Zoom, but at Lehman, every final exam is 2 hours. And the test is designed so that it can be done in 2 hours.
Okay.
Anything else?
No,
No.
Professor, that's all. Because I know in the exam 2 what happened to me. Problem number 6, I did only part 1A. On the other hand, 7 and 8, I did full, but you didn't count 8 because you only count past 6. That's the problem I had.
Well,
Yeah, I know. So in the final, I have to be little careful.
well, on the final, there won't be a choice. It'll just be do everything. So,
Everything. Okay.
okay, I gotta go. I'll be
All
back.
right, Professor. Thank you very much, Professor.
All right. Bye, everyone.
Thank you very much, Professor. Enjoy the rest of your day.
Thank you. You too.